Okay, I want to start talking about probability because probability comes up a lot in management decision making. I'm going to begin with just a really basic example of how this can be. Let's take a look at this situation that airlines find themselves in. They have to sell a certain number of seats, and what they found over time is that people tend not to show up. So let's take a look at the decision-making scenario that they find themselves in. So if we were to just take a real rough guess of what their situation looks like, we can kind of try to graph uh, their the probabilities that a certain number of people will show up. So let's say that they're selling, let's say 200. They've got 200 seats on an aircraft, and um, it could be the case that 100% of them show up. So we'll call this endpoint. This is 100%. And so this axis will represent the percent of passengers who show up. And this axis will represent the probability of that number of passengers showing up. So we haven't really defined probability or given units yet, but let's just say that it's the probability or the odds or the chances. We'll leave it unitless for now, and just so that we can look at relative high or low. So the probability that 100% are going to show up, it turns out from record keeping in the past that it's fairly low. Let's say it's there. And the probability that none of the passengers will show up is also going to be fairly low. So it'll be over there somewhere. And we can say, okay, well, if 100% is low, how is 99%? Well, that's going to be higher, obviously. And, say 95 is going to be higher still. And going from this end, we can say 10%, still fairly low, that only 10% will show up, but it's going to be higher than 0% showing up. So we can see from this trend that at some point there's going to be some peak. This function is going to have a maximum, let's say there. And let's just say that this maximum occurs at, say, 85%. So what this says is that the most likely scenario is that 85% of these 200 show up. So the most likely scenario is 170 people show up for a 200-seat aircraft. So then what do we do with that information? So we've been able to calculate this probability, and knowing this probability lets us take some strategic sales position. So for example, how many seats should we, if we sell 200 and only 170 show up, that's good, but it would be better if we could fill that aircraft and oversell. So sell more than 200. So if statistically 170 are going to show up, then how many should you sell? Well, okay, so we want to say, okay, well, 85% will show up. 200, let's say we fill the aircraft, this would just be a ratio. We'll say, well, 200 is what percent? 200 of what? 200 is 85% of what? And so this is a fairly simple ratio. And it turns out that this winds up being somewhere in the neighborhood of 236 or something like that, 235. So you can sell 235 based on these probabilities. Okay, so this is just one example of where probability works into a business decision-making process. Now, a lot of people get angry about this when they find out that airlines oversell these tickets, but you can see that this is just reasonable decision-making based on what they've observed in the past. Okay, so then in talking about probability, I want to first of all, just show some other cases where probability might come up. So you might have to make some decision under uncertainty. And anytime there's uncertainty and you can place a probability, you can make better decisions. So for example, what is the probability that an investment will make a profit? And so that probability is the definition of risk, right? So that's obviously a decision that has to be made quite a bit. What is the probability that a project will be completed on time? Projects are late, they're frequently late, but if you can place a probability on that, you can arrange resources appropriately. What's the probability that 3 of the next 40 shipments will be late? That's a sort of problem that we'll be able to solve after the next lesson. Or what is the probability that fewer than 200 customers will arrive today? So my daughter works at a diner, and the manager there has to make decisions about how many people to put on the staff. And so if they say, well, the average for a night like this would be 200 customers, can you put a probability that more than 250 will show up, for example? Okay, so probability is an important thing to understand, and the better we can use it, the better our decisions will be. Okay, so we're going to talk about classical probability, and classical probability is a set of methods and techniques and frameworks that have existed for a long time, and they emerged from playing games. Now, games are a lot more complicated than simple probabilities of outcomes. But for this lesson, we're going to concentrate just on probabilities within games. Getting into more complicated issues of strategy and luck and personality, we'll get into game theory, which is outside the scope of this course, unfortunately. Okay, so this is a picture of the Gruss family game setup. And I picked some random pieces out of these games to talk about probability and calculating probabilities. Okay, so let's take a look at a simple example that I think you'll be able to answer right away without having any kind of background whatsoever. So let's say I were to put 3 cards from a regular 52 card playing deck down on the table face down. And if I told you that that here we've got one of these there are 2 black ones. So we've got a black one and a black one and a red one. And if I were to tell you, okay, so 2 of these are black, we don't know which ones, and one of them is red, what is the probability of drawing a black card? Okay, so you can probably say this right away and just say, okay, well that's going to be 2 out of 3, and that's a very intuitive, simple kind of problem that you've known how to do forever. But embedded into this number is several concepts of classical probability that I want to go into in more depth. When we formalize the intuition that went into a conclusion like this, it gives us a framework that we can use to go into more complicated problems, which we'll look at later in this lesson. Okay, so let's think about what we're doing here and put formal definitions on this. Okay, so what we have here in this whole scenario where I say, okay, draw a card, we have something called a random experiment. So we start off with some kind of experiment where we're going to do a test, we're going to run a trial whose outcome is determined by randomness. Okay, so we formally call that a random experiment. And a random experiment is going to have an outcome. Okay, so in our case, the random experiment is drawing a card, right? And the outcome that we asked about is drawing a black card. Okay, so if we were to think about all possible outcomes, then we have what's called our sample space. Sample space. And the sample space in this case, so what are the possible outcomes? Well, we could have drawn a red card, and we could have drawn a black card, and that's it. This is our whole sample space. It's either one or the other. And we see that this outcome is just like a random selection from this sample space. Okay. Now, we also have what's called an event. An event is some set of outcomes. So it's a set of outcomes that we can assign a probability to. Okay? A probability. Okay, so what is the difference between that and an outcome? Well, we might say, okay, well, drawing a black card is an outcome, but it's also an event because we can put a probability on that particular outcome. But an event, so this would be called a simple event. An event with only one outcome of the random experiment. Okay, but we might also say, okay, well, what is the probability of drawing two black cards consecutively? Okay, so this would be called a joint event. So there's only, in the simple event, there's only one outcome, and in the joint event, we're looking at two outcomes. And later on in this lesson, we're going to look at several different kinds of joint events. Okay. So also embedded in this conclusion is some other insights about what we mean by a probability. So let's think about what is the possible range. So let's think about the range of values that this probability can take on. Well, if I were to say, the maximum number of black cards that I can put in here is 3. So if I were to put in 3, and I were to say, what's the probability of drawing a black card? Then you could say, well, that's 3 out of 3, which is equal to 1. Okay, so this is going to be the maximum value of probability. Probability can only go up to 1. Okay, so let's think about, well, then on the other side of this, what's going to be the minimum probability? And if I were to put in 3 red cards, then we would have, there are 0 ways to get a black card. So we would have 0 out of 3, and so that would be equal to 0. Okay, so we have here a range then. So a probability can range from 0 to 1 inclusive. Okay, so that's so again, in this rather simple game that I set up here, we see examples of these various formalisms, and we also see that probabilities can have a range going from 0 to 1. Okay, so another thing I want to look at and formalize a little bit is, well, how did we come to this 2/3? What was the algorithm of actually coming up with that, so that we can carry that to more complicated problems? Okay, so what was the numerator? So when we were making that numerator, when we decided, so we've got a numerator over a denominator. When we decided about this 2, what were we doing? We were saying, okay, well, given that what we want is a particular outcome, that is, we want to have a black card, what we were saying is, how many black cards are there? Or the number of ways of getting a black card, or the number of ways of getting the outcome of the black card, which was 2. And then in the denominator, we're looking for the total number of outcomes. Okay, so there are 3 possible outcomes here. 2 of them are black, and so that's how we arrived at 2/3. Okay, so when we are trying to find out what is the probability of an event, we need to find out the number of ways of getting that event. Okay, so the number of ways of getting the event, and then divide it by the total number of outcomes in the sample space. Okay, now in the next lesson, we're going to get into how complicated each of these can be. So finding out the number of ways that an event can occur is not always straightforward. And likewise, calculating the total number of outcomes is not straightforward either. So in the next lesson on counting rules, we're going to get into some of the ways of doing that and some of the other strategies. Okay, well, so we've taken a look at how to go about calculating a simple event. And remember, a simple event is just looking for the probability of one outcome. Let's say we wanted to look at probabilities of multiple events together. Okay, so let's say usually you use letters like this you assign letters to certain events. So let's just say, okay, event A in this case, we have a set of marbles. And the event A is that you draw, without looking, a blue marble. Okay, so the event is that you draw a blue marble. And let's say there's another event of interest here, event B. And this is going to be drawing, let's say, a green marble. Okay. So now I might ask, okay, what's the probability of A? What's the probability of drawing a blue marble? Okay, well, again, using the same intuition that we used last time, we can say, well, the number of ways of drawing a blue marble, so that's 1. There's only 1 blue marble. And we divide that by the total number of outcomes in the event space. So in this case, there are 1, 2, 3, 4, 5, 6 marbles. Okay, so the probability of event A is 1/6. Okay, and that satisfies the range criteria. That's somewhere between 0 and 1. Okay, and so now we can look at probability of outcome B, probability of event B. Okay, so green marble is the same. There's only 1 green marble, and there are 6 total marbles. Okay, so this is simple enough. But then, what if I were to ask about something like, okay, what's the probability of A or B? What's the probability of drawing either a green marble or a blue marble? An alternative notation for this is probability of A U, and that's a U for union, probability of A union B. So this is the same as OR, that symbol right there. You can think of it as a U, although we'll have an inverted U for something else later. So what's the probability of A or B? Okay, well, if we think about this logically, that if we were to say A or B as a, just one single event, we could see that there are 2 ways of getting that, 2 ways of getting a blue or a green out of 6 possible outcomes. Okay, but we have a property of this particular setup that makes it nice and easy to calculate this, and that is the fact that each of these events are mutually exclusive. There is no way for these 2 events to occur simultaneously. So this property, mutual exclusivity, makes it fairly easy to calculate this joint probability, this So the probability of A union B here is just going to be equal to the probability of the first one plus the probability of the second one. Okay, so in this case, this would just be 1 out of 6 plus 1 out of 6, so 2 out of 6. Okay, so this property of mutual exclusivity makes it possible to simply add these two up when we're interested in coming up with the the union, the probability of A or B. Okay, so to make it a little bit more formal, this what does it mean to be mutually exclusive? Well, in addition to asking about probability of A or B, we can ask about the probability of A and B. And another notation for this is probability of A intersect B. So in set notation, this means intersect. So the probability of A and B, and what is this here? So the probability of drawing a marble and it being both blue and green is, of course, 0. So this is what mutual exclusivity means. It means that the probability of the intersection is equal to 0. Okay? All right, so let's take a look at another joint event that adds a little bit of complexity to this. Okay, so this time we're going to take a look at a deck of cards. This is the standard deck of cards. We've got 4 suits and 2 different colors. And for each suit, there are 13 cards. Okay, so let's take a look at some events here in this situation. So let's say event A will define, and let's use colons so we don't get into problems here. So event A will define as from a shuffled deck that's drawing a 3. Okay, and event B from a shuffled deck is drawing a red card. Okay, so once again, you can come to the the simple and marginal probabilities without too much trouble here. So okay, so the probability of drawing a 3. So we just use that same formula, the number of ways of getting an outcome divided by the total number of outcomes. Well, the total number of outcomes is very easy here. We just know that it's 52. So the probability of A is equal to something over 52, and it's going to be the total number of ways of getting a 3. So we see here, these are our 3s, so there's just going to be 4. Okay, so 4 out of 52. And the probability of B is, once again, total number of outcomes is 52. And how many of those are red? Well, half of them, which is 26. So 26 out of 52, which is just 1/2. Okay, so now, when we're dealing with a joint event, that is, event that consists of 2 outcomes, when we are looking at just the event of each individual one, there's a term that we use for that, and that's just called marginal probability. The marginal. So the marginal probability of A, we look at the joint probability of A and B, but the marginal probability of A and the marginal probability of B. Okay, so we've got these marginal probabilities. Now let's get into some more interesting questions. So let's say I want to know, what's the probability of event A or B? Okay, so now we don't have mutual exclusivity anymore here, do we? We've got a situation where we can have a card that is both a 3 and red. There are 2 of those. So not having mutual exclusivity anymore means that we can't just use that simple addition rule anymore, probability of A plus probability of B. So we have to figure out, well, how do we figure out this particular joint probability? Well, let's think about why we can't do that. Why we can't just do what we did before. Okay, so let's do a Venn diagram to represent all of our outcomes. So I've got this. This is my sample space. All possible outcomes. Sample space. Okay, and so some of these, let's say, we're going to have this. So this is going to be all of the outcomes for A. Okay, so A, remember, A is the 3's. Yes. So these are going to be the outcomes that are 3's. Okay, and we're going to have the outcomes that are red, which are going to be like this. Okay, so why do they overlap? Well, so we have, these are the 3's, right? And these are the reds, and we're going to have ones that are both 3 and red in here. Okay. Okay, so let's think about what would happen if we were to just apply our addition formula. So if we were to say, okay, probability of A, okay, so we're going to be, let's see, okay, so we're going to count all these. So this is probability of A. And then we're going to add up okay, plus probability of B. So we're going to add up all these. So we've got a bit of a problem here, because this region in here, we have managed to count twice. Okay, so these were counted twice. So no big deal, just take it back out again. Okay, and so what is this? Well, these are the outcomes that include 3's, cards that are 3's and red. So what we have to do is just take out those. So this is the probability of A and B. Okay, or remember I said that this would be intersect B. Okay, so now we have a more generalized way of coming up with a probability of A or B. All we have to do is subtract out the intersection of A and B. Now, the reason we didn't have to do this before in the case of mutual exclusivity is because the probability of A and B was equal to 0. But it would still work here, because if we use this formula, this would be 0, and we would just have the sum of these two marginal probabilities. Okay, so let's go ahead and calculate this then. So the original problem was we wanted to know what was the probability of A or B. Okay, so all we have to do is now figure out, okay, probability of A, add it to the probability of B, and then subtract out their intersection. Okay, so the probability of A, we already calculated it, 4 out of 52. Probability of B, we had 26 out of 52. Okay, now what's their intersection? Well, this we can get just by our old rule of counting the number of ways a certain event can occur and divided by the total number of outcomes. Okay, so of the 52 possible outcomes, how many of these are both red and 3? Well, it's 2. Okay, Okay, so this is how we go about calculating. So now we've got two ways of calculating joint probabilities. We've got the probability of A and B, and now we know with this formula how to calculate the probability of A or B. Okay, so this looks like it would be 28 out of 52. Is that right? So 30. Okay, so this would be 30 minus 2, so 28 out of 52. So 28 out of 52. So that's the probability of drawing a 3 or a red. So we can tabulate these insights to make it convenient for a number of calculations. So I've got a table here, and this is called a contingency table. And this is a way for us to organize the events, these two events for which we're interested in some kind of joint probability. So we've got event A, again, this is the event that we draw a 3, and event B, the event that we draw a red. Now, so if the event A is that we draw a red, the event not A, which is denoted A prime, is called its complement. So the complement of A is that we draw something that is not a 3. Okay, so we're going to set up this table so that we assign a probability to A and a probability to its complement, and likewise a probability to B and a probability to its complement. Okay, so let's start off by looking at what goes in these cells. So these are going to be, in this cell up here, we're going to be looking at the probability of A and B both occurring. So this cell is going to hold probability of A and B. Okay, so the probability that we draw a 3 and that it's red. Well, how many reds were there? How many red 3s were there? Well, there were 2 out of 52 possible outcomes. Okay, so this then is going to be, in this cell, we're going to have the probability of A and not B. Okay, so what does this mean for our example? So this means the probability that we draw a 3 and that it is not red. Well, it turns out that there are 2, right? There are 2 black 3s. So 2 out of 52 outcomes are going to be both 3s and not red. Okay, so what we do down here is we do the sum of these. Now, so this is going to be, let me just draw an arrow because I don't have quite enough room here. So in this cell, we're going to put the sum of these two. So that's going to be the probability of A and B plus the probability of A and not B. Okay, now because by definition B and not B are mutually exclusive, this is really just probability of A, right? Because these two situations exhaust all possibilities in which A appears as an outcome. So we get an A and it's either going to be B or not B. It's either going to be red or not red. So this is just going to be probability of A. So the probability of A, and so we can just sum up these. So probability of A is going to be 4 out of 52. And so that makes sense because the probability of drawing a 3 is going to be 4 out of 52. Okay, so let's go ahead and fill in the B's now. So the probability of B, well, first of all, I think it might be easier. So remember that when we're dealing with just one particular outcome, one of the events in a joint probability, we call these marginal. And you can think about it this way, that they're in the margin of this table. So anything here and here and here and here, these are going to be marginal probabilities. Okay, so that means then we can go ahead and take a shortcut and just put down our marginal probabilities here. So this is just going to be the probability of B. This will be the probability of not B. And this will be the probability of not A. Now, we know that the sum total of all of these things has to be 1. So when we add these all up, this is going to be 52 out of 52. So this lower right corner is just always going to be 1. Okay, so because these two events are mutually exclusive and exhaustive, we know that if there are 4 cards that are 3s, that means there's 52 minus 4 out of 52 that are black. Sorry, that are not 3s. So the probability of a not 3 then is going to be 48 out of 52. Okay, and now these sum up to 52. Okay, so what is the probability of B then? So the probability of B, the probability that we draw red, we already know that there are 26 cards out of the 52 in the deck. Okay, so if we know this, then we know that these two have to add up to this, right? So we can take a shortcut to the calculation of not A, so that is not 3 and B, but let's just take it, so because we're going to go row wise, let's just say, okay, so the probability of B and not A. Probability of B and not A, okay? B and not A. So that means the probability that it's red and not a 3. Okay, so we know that there are 13 cards, right? And we know that there are 13 cards per suit. And we know that there are, we know that there are 26 cards in the red suits, 13 cards per suit. And we know that 2 of those are going to be 3s. So that means it's going to be 26 minus 2, which, as we saw, these two have to add up. So it's going to be, so there are 24 cards that are red and not 3s. Okay, so B and not A. Okay, so down over here, this is probably the hardest one to conceptualize. So now we're dealing with the probability of not A and not B. Okay, so that means the probability that it's not a 3 and it's not a red. Okay, so in this case, it might just be simpler to just work backwards from the marginal probability. Okay, so what's the probability of not B? So the probability of a card not being red, well, is just 26 out of 52, half the deck. Okay, and so we know that there are 2 cards that are not red and are 3s. So that means there must be 24 cards that are not 3s and not reds. And so these add up to 1 and these add up to 1. Okay, so I've got this filled in. So in the interest of neatness, I've got this same contingency table filled out here. I did it by hand here, but I've also written in the answers here, so you can refer to it. I believe these are correct. Okay, one more concept I want to go over before we leave classical probability is this idea of conditional probability. So remember that in looking at joint probabilities so far, we've looked at two different ways of relating the two different events of interest. We talked about probability of A union B, which is the same as probability of A or B. So the probability of either of them happening, and we looked at the general rule for that. Once again, real quick, is just probability of A plus probability of B minus the probability of A intersect B. Okay, and we looked at the probability of A intersect B also. And we just did that with our usual rule of the number of ways that these two can happen divided by the total number of outcomes in the sample space. Okay. So there's one more operand for relating these two, or operator for relating these two events, and that is the conditional probability. So in this case, we're talking about the probability of a certain event, let's say A, given that a certain other event has taken place. And so we can think about this. So if the union is or and the intersection is and, we can think of this as given. This operator's word is given. So that's what this bar means. Okay. So there's a difference between the probability of A and B and the probability of A given B. Okay. So in this case, for this question, we're not given that either of them has actually occurred. We want to know what's the probability that they both will occur. But in this case, we're asking what is the probability of one event given that we know that something else has happened. So they're not the same. These two are not the same, but they are related by a fairly simple formula. It turns out that the probability of an event A given that another event B has occurred is their, remember this is their intersection. So it's going to be their intersection divided by the probability of what's given. Okay, so there are ways to show this with trees and so forth, and you can probably find some videos about that, but I found that that's not really necessary for our purposes. As long as we understand that the probability of A given B is equal to the intersection divided by the probability of what's given, then that will be enough for our purposes. So let's take a look at a problem where a joint probability that is conditional comes up. And I've kept this formula up here so that you can refer to it. Okay, so let's say we have a used car lot here, and we know that 70% of the cars have air conditioning and that 40% have GPS in them. And we also know that 20% of the cars have both, that is both air conditioning and GPS. So the question then is, what is the probability that a car has a GPS given that it has an AC? Okay, so let's go ahead and define these events then. Okay, so since we want to use this formula as it's written up here, we want to have B the thing that's given. So let's define event B as that the car has AC. Okay, so the car has air conditioning is event B. And we'll define event A as the car has GPS. Okay, so we've got our two events. So let's go ahead and fill out this contingency table to organize what we know. Okay, so let's go ahead and see if we have enough information to fill in enough of this table that we can deduce the rest. Okay, so let's see the probability. Well, let's start off with the, let's see, do we have a marginal probability for A? So that a car has GPS. Well, so that a car has GPS. Well, we know that 40% of them have a GPS, right? So the probability of the total probability of A regardless of B. So the probability of A in general is 0.4. Okay. Okay, and we have another marginal probability here, right? So we have 70% have air conditioning. So we know that this event B is that the car has air conditioning. So we know that its marginal probability over here is going to be 0.7. Okay. All right, so that, well, where can we go from there? What else can we fill in here? Okay, so the probability that a car has both of them, which is 20%. Okay, so this is going to be the probability of A and B. Okay, so that's going to be 0.2. Now, it turns out we can use a combination of logical deduction and simple math to fill in the rest of this. So we know that these two have to add up to 0.4, right? Because that, if 40% have GPS and 20% have GPS and AC, that would mean that 20% have GPS and not AC. Okay, and we know that these add up to 0.4. Okay, well, so we know this one too, right? Because we know that all told, 70% of the cars have air conditioning, which is event B. And if 20% have AC and GPS, that would mean that 50% don't, so 0.5. And of course, these add up. So we know that the lower right corner has to equal 1, right? So that's 100% of the cars. Okay, so we can get these other joint probabilities by knowing that fact, right? So if 40% have GPS, that means 60% don't. Okay, and likewise, if 70% have air conditioning, that would mean that 30% don't. Okay, because the total probability of an event and its complement is 1. Okay, because it can only be A or not A. Okay, so now we know, okay, so if these have to add up to 0.3, then that's just going to be 0.1. And this works out because these have to add up to 0.6, and that works out. Okay, so now that we filled in the contingency table, how do we go about solving the problem? Okay, so we're asked, what is the probability that a car has GPS given that it has AC? Okay, so if we were to apply this formula, we have enough information to fill it in now, right? Because, okay, so the probability of A and B, okay, is right here. Okay, so that's going to be 0.2. And so it's going to be divided by the probability of B. So you see, we didn't have to fill out the whole table, but it helps. So the probability of B, so the probability that the car has AC, so the probability of B is just the marginal probability of B right here, so 0.2 over 0.7, which is equal to somewhere around 0.286. So somewhere around 30% is the probability that a car has GPS given that it has AC. Okay, all right, so we covered a lot of concepts and the background of probability. Make sure that you review these concepts and that you understand them thoroughly, because we'll be using them more in the next couple of units. So we had a random experiment, and we talked about an outcome, the difference between outcome and event. We defined a probability and what its range was and how to calculate a basic probability. We talked about joint probabilities versus marginal probabilities, mutually exclusive events, what that means, conditional probability and how it differs from other forms of joint probability. And finally, one last thing I want to look at, it's quite simple, is independent events. If two events are independent, that means that their probabilities don't have anything to do with each other. So what this would mean is that the conditional probability, so let's say we've got two events, A and B. So the probability of A given B is equal to the probability of A. Okay? So what this says is that these are completely independent events, that the probability of A has nothing to do with B. So whether we're given B or given not B, it makes no difference. It's just the probability of A. Okay, so if you're given a problem that gives you the probability of A given B and asked to decide whether these events are independent, you can use this simple fact. Okay, all right, as always, good luck and let me know if you have any questions.